Welcome to Solutions, Part 1. Your solution is bad and you should feel bad. So solutions is going to be the basis for all of a lot of our reactions that we do throughout the year. So it's really important that we have a pretty thorough understanding of what's going on as we move forward. So the goals are that you be able to understand the properties of the atom that allow for a solution to dissolve. So what things will dissolve in what, to what degree do they dissolve? Does it completely dissolve? Does it partially dissolve? Those sort of things. You should also be able to calculate the molarity and the molality for a solution, and that does include using a dilution formula to take one solution and dilute it to a smaller amount. And finally, you should be able to write and calculate using KSP expressions. KSP expressions are how you determine the degree of solubility of a particular salt. So a lot of these things are going to be reviewed from your first year of chemistry, but we are going to take it a little bit further than we did in the first year of chemistry. So properties of a solutions, this is all review. You should know that solutes are the things that are dissolved in the solvent. So the smaller one tends to be the one that's the solute. Most of the time when we work with solutions, you're going to have a solid solute and you're going to have a liquid solvent. That's just generally the way we're going to work in this class. But do know that if you have a liquid here and it's the smaller one, that could be the solute as well. So the solute and the solvent is the larger one, the solute is the smaller one. Almost all the time, our solvent is going to be water. Now we will work with some other substances where we are going to have to dissolve it in oil or alcohol, but water is the primary solvent that we'll use in this class. Now, like dissolves like as a general rule. Now, this is a general rule. Polar solutes will dissolve in polar solvents. They have to match. In other words, like dissolves like because those two are alike. And nonpolar will dissolve in nonpolar. Now, I say this is a general rule because it depends. There are certain salts which are polar in nature, or ionic, that won't dissolve in water. So we have to do a quick review here and say, well, what determines whether or not something is polar or nonpolar? And something is polar or nonpolar depending on the electronegativity. Now, you should remember this term from first year chemistry, and the electronegativity is the degree to which something wants an electron. So, normally, when you have a hydrogen and an oxygen that are bonded, remember that bond represents a pair of electrons. Now, we like to think of the electrons as being shared equally, but that's not really the case. Most of the time, one of the atoms will pull those electrons more than the other. So you'll see these electrons being pulled more towards the oxygen. They are still shared, but they're not evenly shared. As a result, you get a negative side of the molecule and you get a positive side of the molecule. Remember, that refers to partial. So it's not a complete plus one, it's not a complete minus one, but it's a partial. So as a result, you have a pole. You have a positive pole and you have a negative pole. That's where we get the term nonpolar. Or excuse me, polar. Nonpolar is where you have the electrons that are shared equally. Say you have two hydrogens that are pulling on those electrons equally. Well, there's no partial negative and there's no partial positive. So as a result, there is no pole or it's nonpolar. So electrolytes. Electrolytes is what happens whenever you have ions that actually dissolve in a solution. So if you were to take sodium chloride and you were to put it in water, which is basically what Gatorade is, if you just throw some sugar in there, if you take salt and you put it into water, it were to separate into its substituent ions. It'll separate into Na and Cl, and those things are no longer near each other. They separate into these ions. Now, the reason why they're called electrolytes is because they actually conduct electricity in solution whenever they do. Now, something that is non-electrolytes will not ionize in solution. So whenever they say Gatorade, it has electrolytes, or Brondo, it has electrolytes, if you were to look at that, that's because it has salt. That's all it's saying is when it says it has electrolytes is that it has salt. So this right here is called a molecular level diagram. And it's really important that you be able to draw these for just about everything that we do this year. So this is a molecular level diagram. So if I were to cover a particular topic, you should be able to picture it on an atomic level. So this is the dissociation. So this is what we talked before with sodium and chloride. You see how it separates, and you have the sodium ions over here, and then you have the chlorine ions over here. Now, one of the things that you should look at is as the water molecules arrange themselves around there, you'll see that the H's are what's close to the chlorine. We'll try and zoom in for that. You can actually see that the H's are oriented around the chlorines. Okay, and then you'll see that around the sodium, you have the oxygens that are oriented around it. And the reason why is those oxygens are negatively charged and the sodiums are positively charged. And the hydrogens are positively charged and the chlorines are negatively charged. So as a result, you have this idea that opposites attract. Okay, let's see if we can zoom out here. Okay, so you should be able to draw these accurate representations of molecular level diagrams. Now this does represent the dissociation of sodium chloride. And that's what we mean. The dissociation is what we mean by dissolving. Okay, next we have electrolytes in solution. Like we said, they just allow something to conduct electricity. This is an electrolytic solution, which means it cannot be pure water. Pure water does not conduct electricity because pure water doesn't have enough electrolytes in the solution. Instead, this has to be something like tap water, which has salt and calcium and chlorine and fluorine all dissolved in it that allow the electricity to move back and forth between the ions. So the strength of the electrolytes can generally be determined using what's called a KSP expression. Anytime you see a capital K in chemistry, assuming it's not an element, it's referring to something called the equilibrium constant. Now, equilibrium is a big topic. That's basically what we're going to be talking about this entire first semester. It's different applications of equilibrium, whether it's solubility product like we're talking about here, or acid base, or we're going to relate it to electricity or gases, but it's the whole idea of equilibrium. So last, this SP is used to define the equilibrium constant. This is a specific type of equilibrium constant called the solubility product. And it's telling you how much stuff dissolves. So whenever you have a solid like AB, that could be something like sodium chlorine, where sodium is the A, chlorine is the B. That right there will dissociate into sodium ions and chlorine ions. But it's determined by a ratio, this K value that's experimentally determined. And you can actually generate a formula for it using this. KSP is equal to A to the A and B to the B. So for example, if you had sodium and chloride, it would be the concentration of sodium times the concentration of chlorine equals some number. And it's that number that's experimentally determined. But if you were to have something like barium chloride, it's BaCl2 because you have to balance the charges. So instead of just writing Ba2 plus Cl minus, that is not the correct expression. Instead, what you have to do is you have to say that there are two chlorines. And how you represent chlorine times chlorine in a mathematical expression is chlorine times chlorine is chlorine squared. So what we have is BaCl, and then the Cl is a squared value. Or let's write it so we can see it a little bit more clearly. BaCl2 plus Cl minus squared. And then equals a number that's experimentally determined. So we have an example, and our example here says the solubility product constant of lead-2 chloride. Now the reason why I know that is lead-2 chloride, and the reason you should know it's lead-2 chloride, is because of the fact that chlorine has a charge of -1. So if you have two of them, you have a charge of -2. Lead has to have a charge of +2. So it says the solubility product is 1.6 times 10 to the -5th. So that gives me my KSP value. And then now I need to write what this solubility product is going to equal. So I say KSP is equal to, well, I know lead chloride is going to go to lead and 2 chlorides. So my KSP expression is going to be Pb2 plus Cl minus squared. We have to square that chlorine value. So now all you have to do is take and plug in your numbers, and you say, wait, I only have one number, and that's correct. You only have one number, so you plug in 1.6 times 10 to the -5th. So now where do the other numbers come from for you to be able to solve? Well, they come from this. If you had, let me go ahead and give me a little bit more room up here. PbCl2 goes to Pb plus 2Cl. If I had an infinite amount of lead chloride, okay, that's a little infinity sign, I could say, okay, if I have an infinite amount of lead chloride, I can look and say some of that lead chloride is going to disassociate and fall apart. Not all of it. I have no idea how much it's actually going to be, so I choose X, which means that I would have infinity minus x left over. Okay, on the other side, I'm going to assume that I have 0 lead to begin with and I have 0 chlorine to begin with. I can assume that because there's nothing else in this water. It's just how much water or lead can I dissolve in water. But for every one of these that falls apart, I'm going to produce one lead, because if one lead chloride falls apart, I produce one lead. But for every one of these that falls apart, I'm going to produce two chlorines. So you get X and 2X. If you can't remember what this is that we did in first year, it's called a Rice chart. You have your reactants, your initial values, your change, and your equilibrium. Okay, so now once you know that, let's go ahead and see if we can zoom back out. Okay, so you have X and 2X as my equilibrium values. So you have X and then you have 2X. But remember, this 2X value that represents the chlorine is a squared value. So X times 2X squared is 4X cubed equals 1.6 times 10 to the minus fifth. At this point, you do the math, you divide by 4, you take the cube root, and you get X is equal to 1.59 times 10 to the minus second, and that's your X value. So now what does X mean? We go back to our Rice chart. We saw our Rice chart says that lead was X. So I can say that this right here represents the concentration of lead. But my concentration of chlorine, which it doesn't ask for in this case, my concentration of chlorine is 2X. So if I want to figure out what the concentration of chlorine is, I have to take my X value and multiply it by 2. And that would give me something like 3.18 times 10 to the minus second. Now, I purposefully did not put units here because we haven't really talked about these units. And that's actually what we're going to do next. The two major units of concentration are molarity and molality. You'll also see things like parts per million, parts per billion, but these are by far the two most common that you'll see in AP. Now, molarity is the number of particles dissolved per liter, and molality is the number of particles dissolved per kilogram. The advantage to using molality is whenever you have a change in temperature. Whenever you have a change in temperature, the water will expand or contract, changing the volume. So just by heating a solution, you can actually change the molarity of the solution. So whenever you have an investigation in which you're trying to change the temperature, or you expect a change in temperature, it makes a lot more sense to do molality. A lot of the investigations that we'll do will have a constant temperature. So this is much more common to see things in molarity. Now, these formulas are seen right here as molarity is equal to the moles divided by the volume, and it's got to be in liters, and molality is the moles divided by the mass, and it's got to be in kilograms. Okay, so now ionic molarity. You do have to be very careful with molarity, because when I say a solution is 1 molar BaCl2, that doesn't mean it's one of everything here. You have to be able to look at the stoichiometry of this as well. Remember, for every 1 mole of barium chloride, there are 2 moles of chlorine. So when you take 1 mole of BaCl2 in a solution and then you allow it to dissolve, now you have 2 moles of chlorine. So you have 2 molarity of chlorine ions, and you also have 1 molarity of Ba2 plus. So the total solution of or the total concentration of ions would be 3.0 molar is the total concentration of ions when you allow it to dissolve. And that all comes from this 1 molar solution. So you have to take things like that into consideration depending on what the question asks you. So let's take a look at a couple of example problems. This first one says calculate the mass of iron necessary to make 250 mils of 0.5 molar solution. This is generally a good review. You should have gotten very good at this in first year chemistry. But remember, whenever you have molar, that means you have 0.5 moles of whatever we're talking about, which in this case is Fe3PO42. And you should be good at writing chemical formulas as well. If not, we need to go over that in 1 liter. So you have 357.48 grams is 1 mole. And you should have gotten that by saying, okay, iron 2-phosphate is this. What's the molar mass of that? 3 irons times 2 phosphoruses times or plus 8 oxygens gives you 357.48. Once you do that, you also have 0.25 liters because you had 250 mils, which when you convert it into liters, gives you 0.25 liters. At this point, you cross out, oops, leave the grams, cross that out, and you should get something like 44.685 grams of iron through 2 phosphate. The next question says how much silver is dissolved when 5 grams of silver is placed in a 100 ml beaker of 0.1 molar solution NaCl. So this is a complicated question. It actually has a lot going on here. The first thing we need to do is look at 5 grams of silver chloride. So in a 100 ml beaker and 0.1 molar NaCl. So this is going to be one of these KSP type questions. So the first thing we're going to do is we're going to say, okay, 5 grams of silver chloride. 5 grams of silver chloride. Okay, now you're going to have to go from grams of silver chloride to moles of silver chloride. And on the bottom here, I'm going to put 0.1 liters. That's my 100 mils. So this right here gives us our molarity of our solution, assuming that we can figure out what our molar mass is there. So silver is 108, chlorine is 35.5. We're going to take those, we're going to add them up, you're going to get 143.5. Once you've done that, you plug that right here, and now you have your molarity of your solution. Okay, with your molarity of your solution, you might be saying, okay, great, that's how much dissolves. I've dissolved all 5 grams. But that's not the case. So we've got to do something a little bit more complicated. We've got to, first of all, get our molarity, which is 0.5 divided by 143.5 divided by 0.1. And we get 3.48 times 10 to the minus second. Once we have that molarity, we need to use our rice chart. Okay, so we use our rice chart, and we have silver chloride, and we go to silver plus chlorine. Now the difference here is we can't just simply plug in infinity and 0 and 0 like we've always done. Instead, I have a specific amount of silver chloride that I'm trying to dissolve. And actually, we probably should just go in terms of moles to make things a little bit easier. And we're going to go ahead and multiply this by our 0.1 term. And we're just going to say 5 divided by 143.85. Sorry, my calculator. 43.85. And this is our 3.48 times 10 to the minus second. So once we have this, that becomes our initial value right here. How much we actually have. We're not dealing with infinity now. We have 3.48 times 10 to the minus fifth. No, excuse me, minus second. Now, instead of, we still have 0 silver. There's no other source of silver other than the silver chloride. But we do have a source of chlorine. And our source of chlorine right here is our 0.1 molar solution. So now our change is still going to be minus x. Our change is still going to be plus x and plus x here. So now you're going to get 3.48 times 10 to the minus second minus x. And then on the other side, we're going to have plus x and then 0.1 plus x. So when we have work with equilibrium, we have to use our KSP expression. Now in this one, I forgot to put the KSP expression for silver chloride on there, so let's just say that it's an easy number like 1 times 10 to the minus 10th. So you're going to have 1 times 10 to the minus 10th equals the concentration of silver and the concentration of chlorine. And in this case, you'd have x times 0.1 plus x. Now if you look, this doesn't play into the expression at all. Okay, so because of that, we can just kind of ignore it. It's just part of our rice chart for organizational purposes. So we have 1 times 10 to the minus 10th equals Now, we taught you a trick last year, but then when you had a minus term and then you were dealing with something really, really, really small, that you could ignore the minus term. And it actually works both ways. You can actually ignore the plus term. So I can eliminate this term right here and make this question even easier by saying 1 times 10 to the minus 10th equals 0.1x. At that point, you'd say 1 times 10 to the minus 11th equals x. Now remember, x represented how much silver is dissolved, so I could say that this is 1 times 10 to the minus 11th molarity of silver. Now this is a tough question, and we will spend a lot more time working with something complicated like this. This one's a little bit easier. It says, what is the molarity of lead if 150 grams of lead is dissolved in 500 mils of water? Okay, as long as you can remember what lead is, then we should be able to get that moving forward. So you have 150 grams of lead 4, which is going to be Pb, and then you have cyanide, and there's going to be 4 cyanides to balance out the leads. So you have 150 grams of that. Okay, you are originally in 500 mils of water, so we'll call it 0.5 liters. And at that point, you would say 1 mole, and then 311.27 grams is what you have for lead cyanide. And then you're in moles. But you're in moles per liter at this point, so you divide it out, and you should get something like 0.964 molar. The dilution equation. So the dilution equation is going to be really, really common, and it works on the principle of if you have a solution that has, I don't know, let's say that's 12 dots. Okay, if you have 12 dots there, you still have 12 dots here even when you add water to it. So you have the same number of particles. In other words, you have the same number of moles. So the mole of one substance equals the mole of another substance. So because you have the same number of moles in both cases, you can say M1V1 equals M2V2. And that comes from a rearrangement of the formula that we use for molarity. Molarity is equal to the number of moles divided by volume. Multiply both sides by volume, you get number of moles equals molarity times volume. Now since the moles are equal, M1V1 has to equal M2V2. So whenever you do this dilution, it really helps to do dilutions on a small value. You really don't want to do more than a 10 to 1 dilution. If you were to look at this particular example, if I were to say 2 mils, given a 2 molar SOx solution, how can you produce 50 mils of 2 times 10 to the minus 6th? So you have a volume 1, because that's what you're trying to get. And on the other side, you have to have 2 times 10 to the minus 6th, and then 50. Well, when you multiply this out, this is going to end up being something like 1 times 10 to the minus 4th equals 2V1. Or V1 ends up being 5 times 10 to the minus 5th. This is an impossible value for us to measure. So whenever you do a dilution, it is imperative that when you do these dilution equations that instead you do what's called a serial dilution. You take 1 mil of this, you add 9 mils of this, and that dilutes it by a factor of 10. Because you went from 1 mil of it to 10 mils of it, that's a 10 to 1 dilution. So instead of it being 2, it's now 0.2. And then you were to do that again, and now it's 0.02, and now it's 0.002, and so on and so on and so on. So in this case, if you were to do this with 6 serial dilutions, it would be much more effective and much more accurate than trying to measure out 5 times 10 to the minus 5th mils. That's just too small of a value for us to do in the lab. Okay. In this case, is you are given 250 mils of a 1 molar solution of hydrochloric acid. Unfortunately, the investigation requires 4.5 molar hydrochloric acid. So how can you reverse dilute the sample? So if you were to have a substance that had, let's call it 5 particles, because we can't do 4.5, and you wanted to concentrate it, you would want these 5 particles to stay, and then you would want to remove the water. Now the problem with removing water from a solution is if you were to use like an aspirator, or you were to try and pull up or pour off some of the water, you're more than likely going to pull out some of the hydrochloric acid or whatever is dissolved in it. But you can use the fact that certain things have different boiling points. And so if you were to try and boil this, you can actually boil the water out and the hydrochloric acid will remain behind. So how much water do you need to remove? Well, in this case, this is what you're given. So I have 1 molar, 250 mils, because that's my M1V1. And on the other side, I have M2V2, and that's going to equal, you have 4.5, and then you have V2, which is what you're trying to figure out. So when you multiply these things out, you end up getting a volume 2 needs to be 55.56 mils. Well, 55.56 mils is less than the 250 mils you originally have. So you actually have to evaporate out about 194 mils of water in order to get this thing to work. So how would you do it? You would just take this thing, you would mark it at the value it needs to be at, and then you would boil it until it gets to that particular point. Okay, so now we're going to talk a little bit more. This is all we touched on this a little bit in first year chemistry, but the idea of spectroscopy. Um, Spectroscopy is focused on the idea that you can have light interact with a material and you can use it to measure things. So we all know white light consists of Rho G Biv, those are the colors of the rainbow, but the reason why something is blue is because the blue bounces off of it. The reason why something is red is because the red bounces off of it. All the other colors are absorbed. So a spectrometer uses this, and what we do is we have a light source and we use something that's called a prism or a grating to select one color of light. We want it to be monochromatic or one color. And once we use that one color to select the wavelength, we shoot it through the sample. Once it's shot through the sample, we can measure how much light it is goes missing. It's bright here, and over here it's more dim. That difference in the light can actually be displayed and put into a ratio that we call the absorbance. In other words, how much light is missing. So the absorptivity. The absorbance is going to depend on three factors. The first one is going to be whether or not that substance actually absorbs the light itself. And that's based on the absorptivity. So certain crystal violet, no matter how much crystal violet you put in a sample, is not going to absorb violet. The reason is because it is violet. The reason why it's violet is because it does not absorb violet. Violet bounces off. So because of that, the absorptivity of violet is going to be 0 for violet light. Okay, so this depends on what the substance actually is. Now there's two different ways it's signified in an equation. It's either signified with a lowercase a, or it's signified with this, which is a lowercase sigma, I believe, and then sometimes it's sigma 0. That's the absorptivity. It just depends solely on what that substance is. It has to do with the electrons and those sorts of things. We'll get into that a little bit later. The path length. The larger the path that the light has to go through, the more likely it is to interact a particle that can scatter it or absorb it. So because of that, the longer the path, the more light's going to be absorbed, and we call that factor B. Now it's measured in centimeters, and if it doesn't say otherwise, it is a 1 centimeter standard. And then finally, the concentration. The greater the number of particles, the more light is going to be absorbed, so we call that concentration C. So far we have A, B, and C, and we put those into Beer's law. Okay, Beer's law has to do with something called A equals ABC. But before we do the actual calculations with it, it says what color of light will be absorbed by the blue solution. It would be red, orange, yellow, green, not blue, and then possibly violet depending on the color of blue. So if you're looking at this saying, what do I want to study this with? Well, remember when you're studying with a spectrometer, you want the light to be absorbed, so you want to move as far away from blue as you can, and red would be the appropriate wavelength to search with it. Here's the Beer-Lambert law. It's the A equals ABC that we talked about. A is the absorbance. It's how much light is missing, and because this is a fraction, there are no units. You have the absorptivity. And the absorptivity is based on what the molecule actually is, and that's usually in something kind of strange like this, where it's molarity minus 1, cm minus 1. Then you have the path length, which is in centimeters, and you have the concentration, which is in molarity. So we have a couple of examples to finish off with, and those examples we have here says you have a 1 times 10 to the minus 6 molar solution of lead nitrate, shows the following absorptions at different wavelengths. Spectrometer uses a 2 centimeter path length. Determine the absorptivity. So I'm looking for lowercase a. So once I know what this is, it tells me that I have a 1 times 10 to the minus 6 molar solution. That's my concentration. I have my absorbance numbers. These are my capital A numbers, and I have my B number. So I'm going to use A equals ABC, but in this case, I'm normally trying to solve for C. In this case, I'm going to try and solve for A, lowercase a. So my absorbance in this case is, I want to know what it is at 635 nanometers. Well, 635 nanometers, if you haven't done the lab yet, is red. So because of that, this is my number that I'm interested in. So I'd say 0.35 equals A times 2 times 1 times 10 to the minus sixth. So when you do this, you get 0.35 equals 2 times 10 to the minus sixth A, and then you divide and solve for A, and A ends up being approximately 175,000, and then it's molarity to the minus 1, centimeters to the minus 1. And our last example says a calibration curve is generated to determine the concentration of red dye in fierce Gatorade. Student generates the calibration curve shown below. What is the concentration of red dye if the fierce red Gatorade has an absorbance of 0.37 at 430 nanometers? So if you look at this, you already have a graph that's generated. And whenever you generate the graph, you have this right here. This right here, this graph of absorbance versus concentration is your A equals ABC. And some people say, well, wait a second. You have absorbance, which is here, and you have concentration, which is here, but there's no place on the graph for this A and B. Remember, once you're doing an investigation, the path length is set. You have a 1 centimeter path length. So the path length is a constant, and the red dye is also a constant. So with those two things being constants, they don't change in the investigation. They're constant at every different point, like the slope is constant at every different point. So when you see this y equals 0.00419x plus 0.008, you should realize that it really should say A equals AB multiplied together, which is your 0.0419, times your concentration, which is your x, and then you have this plus term. And people say, well, why do we have this plus term? Well, the plus term comes from the error in the actual instrument itself. So you have some things like the water and the container itself that will absorb some light. So even if you put 0 red dye in there, the water and the container are going to absorb some of the light itself. So this term is actually accounting for the experimental error. So in this case, if I were to plug my numbers in, I would get 0.37, which is my absorbance number, equals 0.0419, and then my concentration, and then I have to account for the plus 0.0088. So you subtract 0.008 from both sides, divide both sides by 0.0419, and you get 8.62 milligrams per liter. Now people have a tendency to say, oh, well, here's 0.37 and I draw it across and then I come down and that's roughly, that's like 8. The problem is that's nowhere near as accurate as using the actual equation itself. Okay, at this point you should go ahead and summarize the notes for this chapter and be ready to talk about the interactive practice examples.